So, welcome and thank you very much for being here. I hope you guys enjoy. I can tell that although I never came to the ICAM school, I was 6 years ago in other schools, and I immensely benefit from them. Actually, I wasn't in ICAM school, not in Rio though. I was somewhere else. And I can tell you that from the people that I interacted 6-7 years ago, half of them are probably now faculty, and it's very nice when we meet in a March meeting or somewhere else and talk about the school time. So enjoy. Person next to you, you're probably going to have to see them for the rest of their career, so try to be friends and learn what they're doing. So please, this is a school. It's not supposed to be a seminar where you just listen. You're supposed to ask questions whenever you don't know, or whenever you feel that I'm just not telling you the truth. So feel free. And as you know, Professor Hondin in the afternoon will talk about an experimental perspective on iron-based superconductors. I talked to him so we don't overlap too much, but we have some overlap, so we're going to give you different perspectives on the topic to show you how rich this field is and what are the main questions that we're still trying to answer. This is the plan of my lecture. I don't know if I'll be able to go all the way here, and it doesn't matter, but I want you to understand each of the steps, and especially because you're going to hear so much words about non-conventional superconductivity, I want first to tell you what is conventional superconductivity and what we understand about it, and how this is not enough to understand these materials and so many others that are around there. Okay? I hope to use some of the Blackboard, and I will go through some of the ideas that have been proposed for the superconducting state. That's where I will spend most of my time. And in the last lecture, I will tell you a bit more about normal state properties. So let me start with a very brief overview of BCS superconductivity. So some of you have already probably seen that, but this gentleman here in 1911, Cameron-Lyons, found that if you take mercury and bring it down to temperature, so he was using helium to cool down these metals, he saw that there is a very strong drop in the resistivity. As you can see here, I don't know if you can see, but this is 4.2 Kelvin. Okay? And what he was actually, it's interesting when you read about it, because he was not expecting at all this. He was expecting, he wanted to know if this would go to zero, as many would expect, or diverge, as for example, Lord Kelvin proposed. So this on its own is an interesting story, but that's the first discovery, and he got a Nobel Prize 2 years later. Okay? And although this is the most popular property of the superconductor, that's actually what's given its name, I'll tell you that this is not what really defines a superconductor, but the main property that I will tell you is actually what's called the Meissner effect, which was discovered in 1933. The Meissner effect tells you that if you take a superconductor, okay, and you apply a field, it expels all the field from its inside. Okay? And this shows that superconductors are perfect diamagnets, rather than, they are also perfect conductors, but this is a more fundamental property than being a perfect conductor. Okay? And, we don't call them super diamagnets, we call them superconductors. So we usually try to look at this property here. Anyway, so this is where things started, and I'm a theorist. And I must say that I started in high energy, and that was even, I don't think that I had even this view of the periodic table. It's much worse, probably. But, this is from Paul Canfield, and I really like this, because if you want to do condensed matter, you need to understand a bit of chemistry. But usually, right, you think, there's hydrogen, something that looks like hydrogen, something that still looks like hydrogen. Then you have here something that you don't care. Then you have things that are worth money. Then you have here things that probably don't exist anyway, things that nobody cares in the final exam, and things that are bombs and other stuff. So this is usually how most of us think about this periodic table, and it's fine. But now, more and more, we physicists have to be closer to material science to understand new discoveries. And I have actually to start thinking the periodic table in a different way and understand that like a puzzle or like a shelf where you pick up your elements and try to build new materials to learn fundamental physics and maybe arrive at new applications. So this here is just a version of the periodic table where I show you all the superconductor elements. So remember, I can make you can look here at all these red ones. They superconduct at ambient pressure. The ones in green, you have to apply some high pressure to see them superconductor. And there's some of them that are not superconductor. For example, the ones that are worth money: copper, silver, and gold. And one question that I will ask you is, if we know everything about BCS superconductivity, and these all BCS superconductors, why are these three here? Why is copper never superconductor? We'll come back to this point later, okay? So, and I will refer to this periodic table once in a while, and I'm sure Hondin is going to tell you even more about how to play around here and learn something about new materials. But after Caroline discovered superconductivity in mercury, then people start looking for superconductivity in other materials, and you find out that so many elements display superconductivity, elemental materials. Okay? And actually, this is superconductivity over the years. Of course, I'm not putting here some important information, but as you can see, it starts with mercury, then lead, you go all the way here to then niobium compounds and things like that. And all these materials here, I dare to say that we understand, although we still do not know how to predict TC, even for these materials, and I'm going to discuss this a little bit more. We still understand what is the mechanism involved in forming the superconducting state. And there's not a unified language in what is conventional, non-conventional, BCS, and non-BCS, but I will refer to these materials in this talk as BCS superconductors. Okay? And that's the Stone Age of superconductivity. Okay? And what is BCS? Well, BCS stands for these three gentlemen here, Bardeen, Cooper, and Schrieffer. And they developed a theory in 1957 that was the first step towards understanding these conventional superconductors. And that's why it's called BCS. Okay? Now, before I tell you about more details about this theory, do you notice how long it took from the discovery to a theory that was accepted? Almost 50 years. And remember, who lived in these 50 years? Which physicists do you know were active in these years? Just tell me some names. Heisenberg. He actually had a theory for superconductivity. Who else? Feynman. He had a theory for superconductivity. We had several, actually, right? Who else? Einstein had a theory for superconductivity. Landau had a theory for superconductivity. Actually, Landau's theory for magnetism is a result of a failed theory for superconductivity, if you wish. His order parameter was the current, for example. So, lots of brilliant people try to develop a theory of superconductivity. And, I mean, when I say they failed, I don't want to use this in a pejorative way, but just to tell you that this was a very interesting problem. And there were so many developments before BCS came into play. And to motivate you, he already had a Nobel Prize. He's a very known professor. He was a postdoc, and he was a grad student. Okay? So, that just to motivate you how, these guys that probably was taking classes with other people just like you found something major, okay? And they also got a Nobel Prize some years later, 15 years later. Now, what is BCS superconductivity here? Well, this BCS, there is a fundamental quantity here, that is the Cooper pair. The Cooper pair, I will tell you a bit more about it, but it's a bound state of two electrons. And the idea, as in any bound state, if I have two electrons, if they're separate, they have some energy. When I bring them together, I can form a state with smaller energy than when they're separate. They form a bound state. And this is the fundamental quantity in the BCS theory. Excuse me. Now this is not enough. We need to have all the Cooper pairs in different materials to be phase coherent, to have the same relative phase. Now, how does it work? How can you form a bound state of two electrons? Because you know electrons repel each other in just free space. So how can you form a state where they form usually a bound state need an attractive interaction, right? So, for example, if I just put an electron here and I study the interaction with other electrons, if it was free space, I would have the Coulomb repulsion that goes with 1 over r, and this is always repulsive. Now, inside a metal, as you know well, this Coulomb interaction is screened. And instead of going 1 over r, it goes exponentially to 0, but still is repulsive. Okay? And these actually are pictures from a very nice short review by Monthau, Pines, and Ozarich. I don't know if he is here, but he will talk to you more about superconductivity in other lectures. But what they realize is that if you now don't consider the static interaction between electrons, but actually the dynamic interaction, you find out that there is a retarded attraction between electrons, as I'm showing here. This is negative potential, and this attraction is usually enough to create a superconducting state, okay? To create a bound state. And the physical picture for this interaction is very simple, actually. As you know, the electrons, they live on a lattice, okay? And I'm putting here the lattice, and the ions here, the lattice, have positive charge. Now, if an electron comes near these ions, it tends to attract them, right? Now, the key point here is that the mass of these ions is much larger than the mass of the electrons, okay? As you know, proton is 2,000 times heavier than electrons. So, this means that when the electron, this means a separation of energies that is fundamental for BCS superconductivity. Now, when this electron moves away, these polarized ions will not actually be able to return to their original positions before another electron passes by, because electrons are much faster. So, but the electron is going to be attracted by this distortion of charges, and effectively it feels attracted to the other electron that passed. So this is the mechanism behind the attraction. It's an attractive interaction mediated by phonons. What are phonons? Phonons are nothing but the low energy excitations of this lattice. Meaning that you have these ions, and then if I disturb them, the low energy excitations are waves that if you quantize, they are bosons called phonons. And by exchanging phonons, these electrons attract each other, and by attraction they form a bound state. Okay? And that is the idea behind the Cooper pair. And in most of these elemental, in almost all of these elemental superconductors, this Cooper pair, you can now ask about the symmetry of this Cooper pair. And there you find out that the spins of the electrons, they are opposite, they form a singlet. A total spin of this pair is 0. Okay? And they move, the center of mass doesn't move, so one has momentum k, the other has momentum minus k.
From this picture, can you just explain why copper, silver, gold?
Okay, so so I'll just repeat your question. So he asked why copper, gold, and silver are not superconductors. I'll go to this point very soon. Okay? Now,
another question.
So here you're saying they're moving in the opposite direction, but in the previous picture you had one electron leaving and the next one coming out.
Yeah.
How does that work?
Well, because the previous picture is just a cartoon. It's just Tom and Jerry version of the interaction. Okay. It's a good question, but this is just a picture. The real reason why they're moving in opposite directions is because you want the center of mass of the bound state to not move. That's the lowest energy state.
I don't understand the way, because if that picture is in that form, that would be a bonding in the real space, in the space.
Yeah.
But sometimes in some papers, some books say that the bonding is in the momentum space, not the real space.
Sure.
I don't understand that.
that's actually a good point. And as you see, this is a picture in real space. And here I already switch it to momentum space. If you give me a little bit more of slides, I will show you how, it's just, you can look at the things in momentum space and real space, okay? And actually, these pairs in real space, they can be very, very far, they can be very, very deep. These two electrons, they can be as far as thousands of angstroms, or 10,000s of angstroms far from each other. But they still form a coherent pair, okay? But in momentum space, it's just k and minus k. So it's just a matter of convenience sometimes. And I will show you a picture very soon of how the pair interaction, a more complicated pair interaction looks like in real space. You see that it's quite complicated, but in momentum space it becomes much simpler. Okay? So it just depends on the way that you want to look at the problem. Okay? Now, so these are the main problems. These are the main objects that form superconductivity. But there's a very non-trivial thing here that I'm not telling you, and maybe I will just tease you to try to challenge me on that. I told you that there is a small attraction. Is this enough to form a bound state? You guys all took quantum mechanics, right? You solved Schrödinger equation. Just forget about if these two electrons here form a bound state and the center of mass doesn't move, this is equivalent of a single particle problem, and you can actually solve the Cooper problem just using Schrödinger equation. You solve Schrödinger equation for potentials. Put an attractive potential. Do I always form a bound state, a state of negative energy? You tell me that if I had them in 2 dimensions, I can solve that any small attraction gives a bound state. That's what you were told by your advisor, probably, who happens to be me. But other than that, you're cheating. I gave a lecture like that in Minnesota, so. But now, seriously, maybe that's something that we can do, or I can give you a handout of how, just to work out the Schrödinger equation, put an attractive potential, and then you can just calculate when the energy is negative. And actually, as Xiaoyu said here, only when you're in 2 dimensions you find that any small attractive interaction forms a bound state. Are all superconductors in 2 dimensions? I mean, no, right? You know they're not. So how come I'm using this argument here? Well,
you were told by your advisor.
I was told by my advisor, that's correct. Who was told by his advisor, and then we go back to probably Bohr, yeah. But there's actually, that's a very interesting point. What actually makes the system, in every metal, makes the system behave as in 2 dimensions is the existence of a Fermi surface. Okay? If you just look near the Fermi surface, the density of states is constant. Now, you know, I hope, or you probably remember, that density of states being constant is a property of 2D free electrons. And with this mapping, because of the existence of a Fermi surface, any small attractive interaction gives rise to a bound state. Okay? That's a key point that Cooper made when the Cooper pairs were proposed. Okay? Now, there's another thing I'm not telling you, is because I told you how to form one Cooper pair. Meaning that if I have 2 electrons near the Fermi surface, and they have a very small attractive interaction, they will form a bound state. But how come I form a new quantum state with all these Cooper pairs entangled? Well, that's the BCS theory, which I'm not going to go into too much details, but bottom line is that you need all these Cooper pairs to have the same phase. It's a wave function, right? It has phase, and if the phases are just being completely random, you never get a superconducting state. Okay, so this is another key point. Now, the message I want you to take here is that BCS state is a new quantum state of coherent Cooper pairs. So when you see the phenomenon of Meissner effect or zero resistance, this is a manifestation of a true quantum ground state. Okay? And then you can ask how I calculate TC. TC is the temperature where superconductivity goes to 0. In this theory of BCS, you can actually show that this depends on something called the bifrequency, which is the typical energy scale of these phonons, of these lattice excitations. And there is this very known perturbative dependence on the attraction. V is the attractive potential, and rho f is just the density of state. So this is a number, okay? So as you can see, Tc in BCS is usually small. Now, BCS is not the full story. You can do a more complete and actually a very well-defined theory of superconductivity called Eliashberg, which is a very controlled approximation because we have a small parameter. The small parameter, as I told you, is mass of the electron divided by the mass of the ion. That's a small number, so you can do perturbation theory. And more than that, you can throw away some corrections in Eliashberg, so you can actually have a theory for Tc. And I'm going back to the question. Well, if I know a material, you give me an element, elemental material, I can calculate this V for you here, because I know how the electron photon spectrum is. I can calculate this omega d here, and so I can calculate Tc for you. And then if you go back to that question, why then, if you do that for copper, for example, you find a Tc of some smaller than 1 Kelvin. How come we never see superconductivity there? Am I missing something here? Well, yes, what I'm missing here is, as I told you, the repulsion between electrons. So there's another term that I'm not writing here that is called the Coulomb pseudopotential, which mostly just reduces this attractive interaction. And if it happens to be larger than this repulsive interaction here, I don't get superconductivity anymore. Now, that's the point where it's tricky, is that we don't know how to calculate Coulomb pseudopotential. Okay? We can put everything logically, and usually what we do, we adjust that based on our calculation of Tc and the observation. But even if we try to do first principle, we have a serious problem of trying to obtain Tc even of these materials. Now, before proceeding, any questions so far?
So for the I2CBW versus after one dimensional, or
So what?
the Fermi surface is one dimensional, or
No, the Fermi surface is just a surface, right? If the material is layered, then it's effectively two-dimensional. Then the surface is actually just a curve, not a surface. But I will not go there now. But what exactly do you have a question about how to do the problem there if it's two-dimensional?
you mentioned the two-dimensionality of Fermi surface.
Oh no. Okay. No.
It's better if you, because we are recording, and then you keep a microphone on, you repeat the question.
Okay. So I will hand you guys a microphone, and whenever someone has a question, raise your hand, and I will press. Oh, okay. So yeah, please repeat your question.
My question is, since the convention of BCS theory, we have the pairs forming to bound states because of the two-dimensionality of the Fermi surface. And I wonder, in the corporate case, we got essentially like one-dimensional Fermi arcs. I was just wondering whether I can make the analogy between.
Well, yeah, let me just make one point here. It's not the two-dimensionality of the Fermi surface. It's just the existence of a Fermi surface. If you have a Fermi surface, the density of states near the Fermi surface are just constant. Okay? Then I'm saying that this maps into a problem of free electrons in two dimensions. Because the density of states of free electrons in two dimensions is a constant. Okay? It doesn't matter if the Fermi surface is a circle or a sphere. There's another issue here that has to do with something called Mermin-Wagner theorem that says that no continuous symmetry can be broken in two dimensions. So technically, if you're really in two dimensions, you shouldn't see superconductivity. That's never the case in real materials because they have layers that are coupled. Okay? But just the existence of the Fermi surface is important in this case. Now, let me tell you a bit more introduced question. You already have the microphone. Okay.
But what tin and indium have in common, or special? They are in the same column that
Yes.
copper doesn't.
Yeah.
That the column group I think is smaller in copper.
That's a good point. If you look at copper, silver, and gold, they are on the same column, and that has to do with why the Coulomb potential there is different than in the other. And this is actually, if I'm not mistaken, such points were made in the early days of BCS by actually David Pines, if I'm not mistaken. But all I'm saying is that we don't have a first principle way of calculating these guys. Okay?
Why?
Let me see a way to explain why we cannot calculate this.
There are some people who are getting closer to the
Sure, there are advances. For example, the group in Japan by Rotaro Arita, they're doing very nice things of extending VFT calculations to include this. The main problem is how to properly include electron-electron correlation in your first principle calculation. So when you do DFT, these correlations are included in exchange functional. But when you do BCS, you cannot use just this usual DFT, so you have to do some modifications. And how to properly take into account these modifications is a point that is under study. Okay? But it's mostly because we know some Coulomb repulsion, we know the screen interaction, we know the correlations, but we don't know the exact form of these correlations. And we need to include them both to cause the pairing and the repulsion. So I can tell you more about it later. There are some more questions? Wow, okay.
Okay. My question is, can you hear me?
I think you have to turn on, yeah.
Okay. My question is about this statement did earlier that you said that just in 2 dimensions, just in the case that the density of states is pretty much constant around the Fermi level that you can get.
No, okay. What it says that if you have a Fermi surface, near the Fermi surface, the density of states, if we do just an expansion,
right.
Okay, where I have positive particles, density of states is constant there.
Well, okay, but in a case when you have a very strongly energy-dependent density of states, what can happen?
Well,
what's the... Does it work toward helping or not helping superconductivity? In the case that, for example, it would be very, very large,
sure.
still, but very energy dependent.
Well,
strongly energy dependent. How does it work?
Sure.
In general?
My point is that I can get as close as I want to the Fermi surface and do an expansion where the density of states can be considered constant. Okay? And those electrons are the ones that are going to be unstable towards the formation of a Cooper pair. Of course, that then if I want to go and include the full energy range, which is important because this is an instability. If I want to understand the actual superconducting state, I cannot just do this instability analysis. I have to actually construct a ground state. Then this becomes important. And usually, you don't want to have much energy dependence for the S-wave superconductivity here. Okay?
And, can I explain more?
Of course.
Okay, coming back to the point that you said, some of these guys do superconduct, some of them do not superconduct. But in your table, you stress that some of them would superconduct under extreme conditions, under pressure.
Yes.
So how can we predict this?
Very good point.
If it does or does not under extreme conditions, for example. Or
So let me.
What should be these conditions?
Sure. Let me answer your question by asking you a question. What do you think is the highest TC of all these elemental? Let me go back. Okay. For all these materials here, which one do you think has the highest TC? Just guess. Niobium. Okay. No one wants to guess more. It is actually, believe it or not, lithium under pressure. It's superconductors without pressure, but under pressure it has the highest TC. Why? Because of something that I will try to show with this expression here. So, what happens if you apply pressure? You start changing the lattice. Okay? The lattice is what's giving the attractive interaction between electrons. If I'm near a lattice instability, where the lattice is going from one symmetry to another, say cubic to tetragonal, for example. Near this instability, there are two main points, two main effects that happen. This frequency here changes and usually actually decreases, but the interaction, the coupling constant, this V, it increases because the lattice becomes very soft. Okay? And the electrons and the lattice become much more strongly coupled because of the existence of soft modes. Okay? And that what leads to the highest TC. So applying pressure is just a way of changing the lattice, deforming the lattice, and trying to bring this coupling constant up or down. Okay? Now, before BCS, there was this very famous experimentalist named Matthias, or I don't know how to properly pronounce his name, if it was Matthias or Matthias. And he said, he had a set of rules to find new superconductors. And if I'm not mistaken, the first one was don't listen to theories. So, but nevertheless, all my point is that even for BCS superconductors, it's still a current challenge to predict DC for a given material. Okay? But the reason why you have, even at high pressure, why you want to apply pressure is to deform the lattice and try to make it give rise to stop modes that couple to electrons. There's another question over there.
In your point of view, is it possible to study this kind of materials with LDA plus DMFT framework?
Okay. Well, I don't know if my opinion there is very relevant because I don't do LDA plus DMFT. What I can do, what seems in my perspective, and that's a very biased perspective, very promising, I actually just take DFT, okay, and the modifications there to include pairing and possibility of pairing. This has been done by groups in the University of Tokyo, actually, and they go much closer to a good prediction of TC. I don't need for these materials, for the elemental superconductors, I personally think that doing a consistent LDA version of because LDA is just a way of calculating the functional, okay, based on free electron gas, or based on just electron gas, uniform electron gas. We need to have an equivalent of LDA for superconductivity, and you can just do DFT, okay. And I think that's probably, in my point of view, could be interesting if you want to look at just BCS superconductors. Okay? And remember, LDA plus DMFT, as far as I know, hardly goes into superconducting state. They usually talk about normal state. But that's a different point of view. Very good. Any more questions? If I don't go through all my slides, I will feel that I achieved my job, because I want you guys to ask questions. Okay? Okay, so let me move on. So, before we move on, let me tell you about one quantity that is fundamental to understand BCS superconductors, which is called the gap function. So, what is the gap function? If I have this Cooper pair, it's a bound state. As any bound state, if I want to break it, I need to give a finite amount of energy. Okay? This energy scale is usually, we call the gap function. Of course, I told about the one Cooper pair. In a metal, in a superconductor where you have all these Cooper pairs forming a new state, what happens is that the density of states, which was a constant, as this dashed line shows here near the Fermi level, is gapped, meaning that I find no states until the energy delta, then I find a peak in the decay. Okay? So this quantity, the gap function, is very important to understand superconductivity. And actually, that was one of the clues that BCS was right, because the gap was found even before BCS by specific heat measurements or by optical conductivity measurements. But unfortunately, I don't want to go into too many details. Okay? So this is a main property. And before I move on, just a disclaimer. Gap is not a necessary condition to have superconductivity. They're gapless superconductors, but I cannot go into these details, so it's just a disclaimer so we remember about that. But so far, I'm going to just focus on gap. Okay. Now, BCS has an equation for the gap, and maybe, well, I think I can just walk you through this here. Don't need to go to the blackboard. I can if you want. But this equation relates the gap function at momentum k with the gap function at momentum k prime. These here are just interactions. This is just the actual attractive interaction or that you have. And this E here is just the new spectrum, which is the spectrum you had earlier plus the gap. Okay? Now, I'm just telling you that this is the way that you, in BCS theory, calculate this gap as function of temperature. Okay? And I'm just writing this equation in a more friendly form. This is the equation. Just, you can solve it in some limits. When delta goes to 0, this gives Tc. Or when t is equal to 0, you can also solve analytically. Otherwise, you just solve it numerically. It's actually you can do it tonight. You know, I know you guys not gonna go out to enjoy Rio, right? So you can just, when in your hotel, just try to solve it numerically, print it out, put your name. No, I'm joking. But the main point here, okay, is that with this equation here, you can actually calculate the gap as function of temperature, and the onset of superconductivity is when this solution admits for the first time a non-zero gap. Okay? Now, there is a key property here, is the following. Go to the limit where t is equal to 0. Then this guy is just 1. Okay? Now, let me see what happens if delta, I also send delta to 0 equals 0. I get the epsilon over epsilon. This integral diverges, is a law, right? This is telling you that if I take a metal and bring the temperature down, is it too close? Okay. There's always an instability towards the superconducting state. And for this equation here, you can actually calculate the C, okay? You just send delta to 0. As I'm telling you, you have a log here, you always get a finite C. Now I don't want to go into detail, I just want you to keep one thing in mind that will be important later. Look at this equation. This is 1, which is positive. This guy here is always positive, because this is positive, this is positive. Now, if I have a V is the interaction. If V is repulsive, V is positive, you cannot solve this equation. You cannot find positive equals to negative. It's 0. Okay? Now, if I have attraction, V is negative, then this guy here becomes positive, and then I can solve the equation. Okay? That's the key point of an attraction interaction here. That's why I put modulus of V, and then you find a value of Tc. Now, you can go put in your computer and solve this, and that's the curve that you find for gap function as function of temperature. You see this is Tc, it goes up, this is a square root behavior, and then it saturates and goes to a constant value. Okay? Now, this is the black here curve is just the theoretical prediction, and the others are data from niobium, tantalum, and tin. And you see that it goes very nicely on top of this curve. Okay? And how they measure that? Well, I believe that these measurements were via optical conductivity, but you can also try to extract that from the superconducting jump. Now, one of the key points, and probably I think Hondin is going to talk more about it in his talk, is the ratio of the gap function at 0 temperature with Tc. In BCS theory, this is a number, which is 1.76. Okay? Okay, so that is just an overview of superconductivity. Question? Do you have, who had the microphone? Oh, it's here. Okay, sorry.
Can you comment on how the sign of V implies that the symmetry of the gap is S?
That's the second part of the lecture.
Okay.
But that's the main point. That's why I want to show you here why you want to be next. Okay? Now, well, we understood superconductivity and everybody was happy. Now we are happier, I would say. In 1986, Benwards and Miller, these two gentlemen here, found the first family of high-temperature superconductors. And this family is loosely called the cuprates because it has copper. Okay? Now, I'm not going to talk too much about, I'm not going to talk anything about cuprates. I'm going to talk about another family of high-temperature superconductors, which is the arenites. But this is very important. This is still an open question a very open question in the field. And see, they got a Nobel Prize 1 year after the discovery. Now, this is a Time magazine from 1987 talking about the discovery of high-temperature superconductors. Okay? Now, do you see, what do you think of this? This is what they would predict superconductivity would generate. We have these now, right? I don't know, you guys have the Prius, right? You just plug in your car to the outlet and you charge it and you drive it, right? They're nothing to do with superconductivity, but still, it's pretty cool that they got it right. Okay, so these are the high-temperature superconductors, the cuprates, And as you can see, this is a dramatically increasing the value of Tc. You go from the order of 20 Kelvin to the highest one here, 140 Kelvin, which is room temperature superconductivity in the night in the moon. As you can see, the nighttime on the moon is 120 Kelvin. I'm from Minnesota, and I think we have a better shot than Brazil to find high temperature superconductivity, room temperature, because our room temperature is way lower than yours. Okay? But in any case, this year is very high temperature, and what is really important for applications is that you find materials that are above the liquid nitrogen. Because Pascual Pagliuso, he's going to give you lectures about heavy furnace, but he's an experimentalist, and he will tell me that liquid nitrogen is cheap. He brushes his teeth with liquid nitrogen. but helium, if I say helium one more time, Pascual already starts getting goosebumps because it's very expensive, and then he has to fire Priscilla to buy more liquid helium. Okay? So, in any case, so liquid nitrogen, my point is cheap because you can get from air. Okay? And so, even if we get good materials that form good devices,